before we continue talking about finding critical points and that kind of jazz, I just want to kind of backtrack for a minute and do one kind of chain rule problem and then one maybe implicit differentiation problem, just because I feel like it's not a bad idea to refresh our memories. So let's say we have the following setup. We are going to have, let's see, how do I want to do this? Yeah, sure, we'll say that. So let's say that we have the following. F of x, comma y, comma z is equal to x cubed times y to the fourth plus z squared. And we are given that x is equal to s squared t cubed, y is equal to st squared, and z is equal to s to the fourth t squared. We're going to find a couple. Well, yeah, I don't want to do it that way. So I'm going to, yeah. So we want to find the following. We want to find, we'll do two different ones. We're going to find del Jesus, oh my gosh. Sorry. Del F, del T, and del F, del S. And before we can start finding any of these parcels, we have to draw our map. So we're going to start at the top with F. That's the function. That's like the output. And then F primarily depends on X, Y, and Z, right? It's written as a function of X, Y, and Z. And then X, Y, and Z each depend on S and T. You have an S and a T down here, and you have those paths, and then it gets a little bit messy here, but it's fine. So there's our pathways. To find del F del T, we're just going to find all the paths that take us from F to T. So I see three different ways of getting there: through X, through Y, or through Z. So del F del T, and it is a del because F at the very lowest level depends on two variables, S and T. So we're taking a partial derivative, plus not a direct derivative here. So it's going to be the path through X, del F del X, times del X del T, the plus the path through Y, del F del Y, times del Y del T, plus the path through Z, del F del Z, times del Z del T. The rest is writing it out. Well, I should say the rest is finding the partial derivatives and writing it out. So let's find all the things. So del F del X is going to be 3x squared times y to the fourth plus 0. Del X del T is going to be s squared times 3t squared plus del F del Y is going to be x cubed times 4y cubed, or 4x cubed y cubed, times del Y del T, which is going to be s times 2t, or 2st, plus del F del Z, which is going to be 2z times del Z del T, which is going to be s to the fourth times 2t, or 2s to the fourth times t. Let me label these things so you can see them better. This is our del F del X. This is our del X del T. This is our del F del Y. This is our del Y del T. This is our del F del Z. This is our dz dt. Del Z del T, sorry. And then, so I'm taking this question from one of these homework problems from Varn. I will point out that in this question, they ask you to compute something like del F del S, and they ask you to write your answer in terms of just the lowest level variables, T and S. So to finish the problem, which I'm not going to do, you would need to plug in S squared T cubed for every X, S times T squared for every Y, and S to the fourth times T squared for every Z. So that X both have to become S squared T cubed. That Y and that Y both have to become ST squared. And the only Z has to become S to the fourth T squared. So it's kind of gross. It might be worth simplifying just so you don't have to type as much, but it might not be worth simplifying, right? Typing it out is, I don't know, like the simplification isn't hard, but it's just another step in the process. So do the amount of work you think is necessary to make it easiest to type into web work if you are in Varn's class and doing web work problems. All right, let's do the other one. So the nice thing about the other one is we're already halfway done. So if I want to find del f del s, well, it's going to be still del f del x, del f del y, and del f del z, but now we're going to multiply by del x del s, del y del s, and del z del s. So I guess we could write it out. So it's del f del x times del x del s plus del f del y. It's a lot of writing. Del y del s plus del f del z times del z del s. So I'm just going to copy my work from here, right? I know it's the same thing, so it's going to be a 3x squared times y to the fourth, and then del x del s is going to be a 2s times t cubed. Del f del y is the same as it was before. It's going to be 4x cubed y cubed. And then my del y del s is going to be 1 times t squared. And then finally, my del f del z is still 2z. And my del z del s is going to be 4s cubed times t squared. It wouldn't have been hard to compute those partial derivatives again, but I'm trying to kind of reduce the mental load, right? You might as well not do the same work again that you just did if you can avoid it. Questions about any of that? Yeah, so again, depending on how the question is phrased. So this question is certainly phrased as express your answer in terms of the independent variables t and s. So yeah, the next step would then be to plug in this for x, this for every x, this for every y, and this for every z. I don't think I need to write that out. I think you all can imagine doing that. Okay. Got one other thing, and then we will continue on talking about extrema. Let's do one of these implicit differentiation problems. Let's see, what have I got here? Sure, that looks gross. So we're going to find the following. So we want to calculate del w del z, given that x to the 6 times w squared plus w to the 5th plus w times z cubed plus 2 times y times z is equal to, sure, 0. So this problem has already been, they've done one nice thing for you already. They've brought everything to one side of this equation. So we are going to say in our heads or write down on paper, okay, cool. This left-hand side is our function of whatever variables are there, x, w, z, and y. We're going to do this the short way. So to find a partial derivative that would be like using implicit differentiation, instead of doing the implicit differentiation, all we have to remember is the following, that any partial derivative we're trying to find, you're going to essentially flip it over. You're going to say, great, the z thing is on top, the w thing is on the bottom. And it's going to be the partial of f with respect to z on top, the partial of f with respect to w on the bottom, and then it's the negative of all of that. That's all you have to remember to be able to do this the fast way. And then we're just going to calculate both things. So we're going to get, let's see. So on top, our fz is going to be 0 plus w times 3z squared plus 0. Great. Couldn't be any better, really. On the bottom, my fw is going to be a little more complicated. So we're going to get x to the 6 times 2w plus 5w to the 4th plus 1 times z cubed plus 0. Done. That's it. There's nothing else to do. You could do this the long way. You should not do it the long way. You know what? I might have missed that. Good call. I did miss the 2iz there. Yeah. So certainly we should have what else in the numerator? Correct. Yeah, thank you.
Like subtract all the terms that we don't need to like one side and then
Right. So I didn't show that because the equation given to us was already everything equal to 0. But yes, if your original equation is starting off with stuff on both sides, then you first need to bring everything to one side. So let's look at one more example of this. Let's say we have, sure, I'll just make some stuff up. Let's say we have the following, sure, we can use powers. X to the 7th times z cubed plus y squared z to the 4th equal to sine of x times y plus e to the x cubed y squared. That seems sufficiently terrible. Not quite. Plus z to the fourth. Now it's sufficiently terrible. And we're going to find del z del x. We know what it's going to be, meaning we know what the equation needs to be. We need this to end up equaling the negative of, on top, the partial of f, which we haven't written what f is yet, with respect to x. On the bottom, the partial of f with respect to z. But to find f, we have to rewrite this equation so that everything is equal to 0. It does not matter which side you bring things to. You can pick either side. So basically, whichever side has more stuff on it to start with, that's the side I'd probably bring everything to, but it doesn't really matter. Probably just pick the left side because, it feels normal. So rewriting this, I'm going to have x to the 7th times z cubed plus y squared z to the 4th minus sine of x times y minus e to the x cubed y squared minus z to the 4th equal to 0. And that now gets to play the role of f of whatever your variables are, x, y, and z. Now we proceed as usual. So my del z del x is going to equal the negative of the fraction. All right, so fx, I'm just taking the partial of this with respect to x. So it's going to be 7x to the 6th times z cubed. That's a 3, sure. Plus 0 minus the derivative of sine of xy is going to be cosine of x times y times the derivative of the inside stuff, which is 1 times y. Yeah, minus the derivative of e to the stuff is e to the stuff times the derivative of the stuff, and the derivative of x cubed y squared is 3x squared times y squared. And then that gives you nothing. Minus z to the 4th, the derivative of z to the 4th is 0. On the bottom, the partial with respect to z. So going through it again, the derivative of x to the 7th z cubed is going to be x to the 7th times 3z squared plus the derivative of this part's going to be y squared times 4z to the 3rd. Derivative of that 0, derivative of that 0, derivative of that's going to be 4z cubed. I don't recommend distributing the minus sign to either the top or the bottom, but you could if you wanted to. But it wouldn't just go to one term, right? It would be the negative of this, and this. So it'd be negative 7x to 6z cubed plus cosine of xy times y plus e to the stuff times 3x squared y squared. And normally, if you were going to distribute it, you would typically pick to distribute to the top, but either choice is correct. Not both, though, right? If you distribute the negative to the top and the bottom, you're multiplying by -1 over -1, which is like multiplying by 1. So if you're going to distribute that negative sign, only the top or only the bottom, not both. All right, good to refresh our memory of those things. So let's continue talking about finding and classifying critical points of functions of two variables. Yeah. So just as a reminder, whatever. Next week, people in Lee's class, raise your hand, have a midterm on Monday. And then people in Varn's class have a midterm on Friday. Okay. I have printed out a practice midterm that is certainly written with a bent towards Lee's class because that is the material I had to work from. So I think everyone should take one and still use it. If I can, I'll try to come up with something for the people in Varn's class that's more specific to their class as well. But his tests are harder to find copies of. So, yeah, let's continue on with this optimization stuff. Or not optimization yet, although that's on the horizon. Oh, I know what I was gonna say. For those of you in Lee's class, do you know what content is going to be included on your midterm? So everything up into including 9.6? Okay. Then we'll go through it. So we'll do some optimization today, sure, too. So let's say we have the following function. F of x comma y is equal to 2x squared minus y squared plus 4x plus 6y plus 1. And we're going to find and classify, meaning determine if it's a max, min, or saddle point. Find and classify the critical points. So taking the partial with respect to x and the partial with respect to y and setting them both equal to 0. We're going to get for x, 4x plus 4 equal to 0. With the partial with respect to y, -2y plus 6 equal to 0. So here we end up getting, let's see, 4x equal to -4 or x equal to -1. Here we get -2y equal to -6 or y equal to +3. So these two things together give us only one critical point. X is -1 and y is +3. To classify this critical point, we're going to, again, find the thing we talked about last time, which is capital D. The determinant of the Hessian matrix. Not that we need to know that. It's just equal to fxx times fyy minus the mixed partial fxy squared. Or fyx, because we've talked about how the mixed partial in either order gives the same result with very, very, very rare exception that we are not going to encounter in this class. So in this case, fxx is going to be 4, fyy is going to be -2, and fxy is going to be 0. So this ends up being negative. I don't care what. I really don't care that it's -8. I just care that it's negative. And since our D is less than 0 or negative, that means that our critical point is a saddle point. Because D is negative. That's it. There's nothing else to say. If this value is negative, it's a saddle every time. So far, our examples haven't been that interesting in that we haven't actually had to plug in the critical point to the thing we're calculating here because it's just been constants all the way. That's not going to continue to be true. So let's look at some other examples here. Yeah, that's a good example, sure. So let's look at the following one. So let's say our function is function of x comma y is equal to x to the fourth plus y to the fourth minus 4xy plus 2. We're going to, again, find and classify. So we're going to take our partial derivatives. Fx is 4x cubed minus 4 times y. Set that equal to 0. And our Fy is 4y cubed minus 4x. A quick aside. This equation, x to the fourth plus y to the fourth minus 4xy plus 2, I would point out is what we call symmetric in the variables x and y. Meaning if you interchanged x and y, like if you literally replaced this x with y, that y with x, and that x with y, that y with x, you would still have the same equation. Exactly. When that's true, it almost always means that your critical points come in like pairs that are flips as well. Like if 2 comma 5 is a critical point, 5 comma 2 also has to be a critical point. But what it really ends up usually happening actually is almost all your critical points are like 4 comma 4 or 3 comma 3 or -2 comma -2. Like but you have to have like the symmetry there. So if one thing is a critical point, so is the reverse. That's the word. I was like, what's the word I'm looking for? Reverse. The reverse is also a critical point. Okay, so trying to solve this, we just don't get numbers like we did last time. So here we have to be a little bit more careful about how we're going to do this. So usually when that's the case, you try to solve the easier one, but they're the same here. So either one's fine. I'm going to do this. I'm going to say this is going to give me 4x cubed is equal to 4y, and dividing both sides by 4, y is equal to x cubed. And then I'm going to substitute that into the other equation. So I'm going to have 4 times x cubed cubed minus 4 times x equal to 0. I should divide both sides by 4. So x cubed cubed is x to the 9th minus x is equal to 0. You have to be super careful here. We can't bring the x, well, you could incorrectly add x to both sides and divide both sides by x. If you do that, you're going to lose the solution. So don't be dividing both sides by x or y almost ever. Instead, we're going to factor. This factors as x times x to the 8th minus 1 is equal to 0. You could factor this more. You probably don't need to. At this juncture, you can probably see that your solutions are x equal to 0 or x equal to 1 or right. You can factor this a lot more, though. You could factor as x to the fourth minus 1 times x to the fourth plus 1. And then the x to the fourth minus 1 factors as x squared minus 1 times x squared plus 1. And then the x squared minus 1 factors one more time as x minus 1 times x plus 1 times the other stuff. And then you can, oh yeah, I can really now see that 0, 1, and -1 are my critical, well, are the X parts of my critical points, right? Those aren't critical points on their own. They are half a critical point. So if X is 0, Y is going to be 0 cubed. If X is 1, Y is going to be 1 cubed. And if X is -1, Y is going to be -1 cubed. So we get 3 critical points, and they are 0, 0, 1, 1, and -1, -1. And they could, each of them could be any type of thing, meaning one could be a max, one could be a min, one could be a saddle. They could all be maxes, they could all be minimums, they could all be, anything could happen. So we have to test them all. So we're going to find capital D again. So now our fxx is going to be 12x squared. Our fyy is going to be 12y squared. And our fxy is going to be -4. Without just some labeling here. That's your fx, fyy, fx. So now we actually do have to plug in the critical point to see what is happening. So let's start with 0, 0. So we plug in 0, 0. We're going to get 0 times 0 minus 16, which is negative. What does that mean? We get to ride a horse because we have a saddle. All right. So saddle. Let's look at another one. Let's look at 1, 1. So if we plug in 1, 1, now we're going to get 12. Also, oh, good point. Don't multiply this out. Don't write this as 144 times x squared y squared. Leave it as this times this, because if we end up having d being positive, you're going to want to be able to look back at either one of these and determine if those things were positive or negative. So d at 1, 1 is going to be 12 times 12 minus 16. I don't care what it's equal to. I just care that in this case, it happens to be negative or positive. For sure positive, right? 12 times 12 is way bigger than 16. So when it's positive, that means we either have a maximum or a minimum. To check, we go back and look at fxx or fyy. So here I'll point out that our fxx is positive. If our second derivative is positive, that means the function is concave which way? Concave up, like a cup, meaning we have a minimum. I really encourage you to think about it in terms of the concavity, because if you remember that concave up looks like a cup or concave down looks like a frown, you'll know that you have a maximum for concave down and a minimum for concave up. So this is concave up, which means we have a minimum at 1, 1. For the other one here, you have -1, -1. We're going to get now, well, so if we plug in -1 here, we're still going to get 12. So it's going to be 12 times 12 minus 16 again. It's again positive. And our fxx is again also positive. So this is also a minimum at -1, -1. And we have classified all 3 critical points. Sure. We'll do one more and then we'll talk about some optimization, which is really the same thing, just different. Yes. Yeah. Mm-hmm. Mm-hmm. So I'll state, when your capital D is overall negative, saddle, you're done. We don't care about the value of fxx or fyy at all. So if you have a saddle, that's it. These values don't matter. What's essentially happening is they might kind of be the same sign, but essentially in some direction you have concave up, and in some other direction you have concave down. That's what's giving you, but they might not be like perpendicular to each other, but like be like at a kind of weird angle or something. But this is telling you if this is negative, then you have that happening. On the other hand, I'll point out that if D is positive, like I said before, fxx and fyy have to have the same sign. They both have to be positive or both have to be negative, because this has to multiply to a positive thing before you subtract something and still have it end up being positive. That's why you don't have to look at fxx and fyy to determine the maximum. You can just say pick one of them. If it's positive, concave up minimum. If it's negative, concave down maximum. But yeah, for the saddle, doesn't matter at all. Let's look at one more of these. Where'd you go? Yeah. That's a good one. All right, one more, and then we will talk about some optimization. Optimization like we did in 17A, right? We had like some parameters and a thing that I can't think of the name of right now, a restriction of some sort, but there's a different name I'm looking for. Okay, we'll find it. One more. So here our function f of x comma y is equal to a constraint. That's the word I was looking for. 3x cubed plus xy squared minus 9x squared minus y squared. Usual deal. Find and classify. So again, we take our partials. Fx is going to be 9x squared plus y squared minus 18x. Set that equal to 0. Doesn't look great. Fy is going to be 2xy minus 2y. Set that equal to 0. And then work with the one that looks easier, which is clearly the second one. It is much easier to deal with. I can take this equation here. I can factor out a 2y and be left with an x minus 1. So what do I get? What are the solutions to this equation? Either y equals what? Or x equals 1. Now I want to be super explicit about this. 1 comma 0 is not a critical point. Why not? Because if you plug that coordinate into both partial derivatives, they're not both equal to 0. So to be a critical point, you have to be able to plug that point into each of these equations and get 0 out. It'll certainly work here. It will certainly not work here. If you plug in 1 for x and 0 for y, you get 9 plus 0 minus 18, which is negative 9, which is not 0. So I just want to be super clear because sometimes people get really confused about like, oh, I got 1 for x and 0 for y. That means 1 comma 0. No, it's not a critical point. So then we're going to take each of these things and plug them into the other equation to then find the corresponding values that do give us critical points. So if we plug in x equal to 1, well, let's see, then I'm going to have 9 times 1 squared plus y squared minus 18 times 1 equal to 0. Or isolating y squared is going to equal positive 18 minus 9, which is 9, which means we're going to get y equal to plus or minus 3. So we get 2 critical points from x equal to 1. Our critical points here are 1 comma 3 and 1 comma negative 3. Which makes sense, right? If you plug in 1 for x and 3 for y, you'll get 0 here because you'll have 6 times 0. And you'll get 0 here because you'll have 9 plus 9 minus 18, which is also 0. Same thing if you plug in 1 and negative 3. Now we'll do the same sort of thing for y equal to 0. We'll take this equation and plug in 0 for y. So we'll have 9x squared minus 18x equal to 0 because y squared was 0. Factor out a 9x. We're left with x minus 2. So we're either going to get x equal to 0 or x equal to 2. So our 2 more critical points are going to be 0 comma 0 and 2 comma 0. Right? Because the second 0 is coming from the fact that y is 0 to get these x values. And over just like over here, the first coordinate was 1 because we set x equal to 1 to then find these y values. And now we'll do the same thing we did before. We're going to test all of our critical points to see if we have a max, min, or a saddle. All right, so we got to find capital D. So capital D is going to be fxx, which is going to be 18x minus 18. Fyy, which is going to be 2x minus 2. And then fxy, which is going to be 2y squared. Do not simplify this. It doesn't help you really. And in fact, you're probably going to hurt. So let's start plugging in things. So let's do 0, 0 first. Plug in 0 for x and 0 for y. Look what I get. I get negative 18 times negative 2 minus 0 squared, which is going to be positive 36. Or you can just say it's positive, right? You don't actually have to write the number. So it's positive, which means we have to do more work, right? It's either going to be a what or a what? Max or a min. Can't be a saddle. Max or a min. So then we look back at either fxx or fy. Oh, look, our fxx is negative. So we're concave down. So we have a maximum at 0, 0. So if you're in the situation where this is positive, you can look at either one because they have to be the same sign. And if it's negative, we don't care because it's a saddle. I mean, sorry, I should point out, if the whole thing is negative, we don't care because it's a saddle. But yes, you can either look at fxx or fyy. So let's look at 2 comma 0. So d of 2 comma 0 is going to be 2 times 18 is 36 minus 18 is 18. 4 minus 2 is 2. And we plugged in 2. We got, all right, 2 comma 0. Plugging 0 for y, and we're getting 0 again. So this is also equal to 36. But now either fxx or fyy have the same sign. They're both positive. So this being positive means we are concave up, meaning we have a minimum. All right, looking at the last two critical points here, 1, 3, and 1, negative 3. So if we plug in 1 comma 3, we're going to get, so we're plugging in 1 for the x's and 3 for the y's. So 18 minus 18 is 0. It doesn't even matter what this is after I plug in 0 there, but this is also going to be 0. Minus 2 times 3 is 6 squared. That's definitely going to be negative. So we have a saddle at 1 comma 3. Bless you. Similarly, if you plug in 1 comma negative 3, we're going to get the same result because you're still going to get 0 here and 0 here because 18 minus 18 is 0 and 2 minus 2 is 0 minus negative 6 squared is still negative, right? Because it's still negative time, or negative 6 squared is 36 and it's negative of that. So this is equal to negative 36, which is also negative. So saddle as well. And we're done. We've found and classified every critical point of this function. Cool. Yeah. Yeah. Right. And this is kind of the really important thing about it. So whenever D, when you plug in the point, whenever D is positive, that means there's more work to do. If D is positive, it means you either have a maximum or minimum. Whereas if D is negative, you automatically have a saddle. But if D is positive, then we go back and look at the second partial derivative, either fxx or fyy. When fxx is negative, that's like the second derivative being negative, which means the function is concave down. If it's concave down, we have to have a maximum at the top of that concave downness. Whereas over here, the fxx value is positive, meaning we're concave up, so we have to have a minimum for that one. So, but I really want to reiterate because I feel like I've seen students in the past say like, oh, well, it's positive, and we know the positive means you have a minimum. No, positive means it's either a maximum or a minimum, and there is more work to do. And the more work is looking at fxx, or if you prefer fyy, either way. That's the whole story. Yeah. So this is my mixed partial here. So you can actually find it either way. So what I did was I looked at fx. I took the derivative of that with respect to y. So the derivative of this with respect to y is 0 plus 2y plus 0. But you could also do fyx. If you take the derivative of this with respect to x, it's going to be 2 times 1 times y minus 0, or 2y. It's the same either way. Yeah. Thank you. All right, so let's see if we can cram in an optimization problem here. I don't love this one. The one that's more realistic. That's terrible too. There's all these. I guess we'll do one of these. Sure. I had other ones up my sleeve. Oh well. So yeah, we can do this one. Okay. So the idea with optimization is you're going to be given some function of essentially 3 variables and then some sort of constraint so that we can write it as a function of 2 variables and then maximize or minimize it as kind of desired. So here is one typical-ish problem. Yeah, that's fine. So we want to find the volume of the largest rectangular box in the first octant. So we're thinking in the three-dimensional system here we're in, where x is positive, y is positive, and z is positive. Right, like we're living in the first octant here. Right, as I like to imagine, this room is in the first octant if that corner is our origin over there. And then with three faces in the coordinate planes, half the battle here is understanding what's being written. And one of the corners in the plane x plus 2y plus 3z equal to 6. So first, before we start just doing stuff, we're going to draw the picture, even though you don't really have to draw the picture here. So I'll point out that this plane, to draw it, I'm going to find its x, y, and z intercept. So to find the x-intercept, set y and z equal to 0, you're going to get x equal to 6. To find the y-intercept, set x and z equal to 0, you're going to get 2y equal to 6, so y is equal to 3. And to find the z-intercept, set those two equal to 0, and you're going to get 3z equal to 6 or z equal to 2. So here is part of my plane. Right, you can imagine it extending in directions. And then what we're saying is one of the corners of this rectangular box we're trying to draw is on this plane. So like there's a corner here, and then our box looks something like this. And mine looks maybe a little too cubish for my taste, but oh well. So that's the idea, is that your box is living in the first octant with three of its faces, the bottom face, the back face, and the left face on the coordinate planes, and then one of the corners on this other plane that we've described. Okay. We want to maximize the volume. That is what you're trying to do. So we want to maximize the volume of the box. So what are we going to do? We're going to call the edges of the box x, y, and z. So then our volume equation is going to be x times y times z. And bummer of all bummers, this is a function of how many variables? 3. One too many. So we need a constraint. Fortunately, we have a constraint, right? Our constraint is that that point there has to be on the plane. So it must also be true, our constraint is that that equation has to be true. X plus 2y plus 3z equals 6. And then what we get to do is isolate one of these variables and then plug that into this equation to get an equation of two variables. Now, we're going to make a choice here based on either comfort or ease of calculation. What do I mean by comfort? Well, I imagine most of us would prefer to do this as a function of x and y. It just feels the nicest. But I would point out that if I was going to isolate one of these variables, isolating z to get things in terms of x and y is kind of the least nice choice I can make, right? I would much rather isolate x. So let's do that instead. So we're going to say that x equals 6 minus 2y minus 3z, and we're going to plug that in for x here. So our new volume equation as a function of just y and z is going to be equal to what was x, which is now 6 minus 2y minus 3z, times y times z. And I do think it is definitely in our best interest to multiply this out before we start trying to find any critical points by taking partial derivatives. So if we multiply this out, yeah, we got enough room. I'm going to have 6 times yz minus 2y times yz. So that's going to be minus 2y squared times z. And then minus 3z times yz is going to be minus 3yz squared. And now we're ready to take some partial derivatives. Specifically, the partial with respect to y and the partial with respect to z. So our first partial derivative here is going to be, let's see, 6z minus 4y times z minus 3 times z squared. Not looking great. Our other partial derivative is going to be 6y minus 2y squared minus 6yz. We're going to set both of those equal to 0. So they both look equally complicated, so I'm just going to deal with the first one. I notice in this first equation and in the second equation, actually, that I can factor something out. In this first equation, I can factor out a z. So I can rewrite this as z times 6 minus 4y minus 3z is equal to 0. Similarly, here, I could factor out a y and get y times 6 minus 2y minus 6z equal to 0. So, bad news. There's going to be 4 critical points. Good news. 3 of them are going to be obviously not the right choice. Here's what I mean. So one solution to this equation would be z equal to 0 and y, or should I say, one solution to this system of equations would be both z equal to 0 and y equal to 0. So potential solutions here. I'm going to need more paper. Yeah, let's just use more paper right now. Put these equations down again. So I have z times 6 minus 4y minus 3, z equal to 0. Okay, so one solution would be z equal to 0 and y equal to 0, which would be the point 0, 0. But that's not going to be the right solution. Why? Well, because if one of the coordinates or one of the lengths of one of the sides is 0, how much volume are you going to get? Not the maximum amount for sure. So we know that this is not the right answer. Similarly, if I say, well, in this equation, I can set z equal to 0. And then if I plug that in over here, I'll get 6 minus 2y minus 0 equal to 0. And then I'll get 6 equal to 2y or y equal to 3. And again, why did I even bother doing the work? Because we know that one of the things is still going to be 0 and we're still going to get 0 volume. In a similar way, if we set y equal to 0 and then plug that in here, we'd have 6 minus 3z equal to 0 and you get z equal to 2. And again, just like this critical point, 3, 0, and this critical point, 0, 2, are both not going to be the right answer because they're both going to give us 0 volume. So these 3 answers, these 3 critical points, while they are critical points, are not going to be the ones that maximize the volume. There's one left to find, and that's where both this factor and this factor are both equal to 0 simultaneously. So we want to solve 6 minus 4y minus 3z equals 0 and 6 minus 2y minus 6z equals 0. Yeah. So what I would probably do is, sure, I can do it that way. I'm going to multiply this first equation by -2 and then add it to the second equation. That's the thing people do, right? So multiplying this equation by -2, I get -12 plus 8y plus 6z equal to -2 times 0 is still 0. And if we add these equations together, 6 plus -12 is -6. -2y plus 8y is 6y. And -6z plus 6z is 0z. This is called the elimination method, where you're eliminating one of the variables. And then if we solve for y, 6y is equal to 6, which means y is equal to 1. If you had preferred, you could have instead said 6 minus 4y is equal to 3z, and then divided by 3. 1/3 times 6 minus 4y is equal to z, and then plug that into the other equation and said 6 minus 2y minus 6 times that. That seemed less nice to me. But this would still give you the same result, that y is equal to 1. So then if y equals 1, well, now we can use one of these equations to solve for z. So if y is equal to 1, I'm going to plug it in right here and say 6 minus 2 minus 6z is equal to 0. So 4 is equal to 6z, or 4 divided by 6, or 2 divided by 3 is equal to z. That should be the y and z value, so find the x value, that maximizes the volume, because it's going to give you a non-zero amount of volume, and the other ones gave you 0. So then to finish out the problem, now we're going to find the x coordinate. We're going to go back to our constraint way up here. Like, oh yeah, x is equal to that. So x is equal to 6 minus 2y minus 3z, which is going to be 6 minus 2 times 1 minus 3 times 2/3, or 6 minus 2 minus 2, which is 2. We found all the values. Did we answer the question? The question was find the volume. We have not answered the question. We found the dimensions, but we have to multiply them together to actually find the volume. So our final answer is that the volume evaluated at, sure, I'm writing things here that are not really. The volume is equal to x times y times z, which is going to be 2 times 1 times 2/3, which is 4/3. So that's the idea of an optimization problem. Similar-ish to how we did it in 17A, but now there's like an extra variable in play. So just like before, you'd have kind of have a function of 2 variables, you'd have to have a constraint to get rid of one of the variables. Same idea here. Now we have a function of 3 variables, we need a constraint to get rid of one of the variables, and then we carry on.